Space weather, usually when we talk about that, it's really the story of our star, and almost any star really that's pretty active. A lot of the things we talk about space weather start on our sun, solar flares, big giant explosions in space, or coronal mass ejections, sometimes called CMEs. That's actually part of the sun being released off of it.
The coronal mass ejections. These can be billions of tons of material that come shooting off of the corona, or the outer layer of the sun, and they can go racing towards Earth and create space weather, both here on Earth as well as places like the Moon and Mars.
And then what we really start to think about is how is that impacting us here on Earth, spacecraft across the solar system, eventually humans on Mars. A lot of that kind of impact story is a lot of where we focus our attention within space weather. Your GPS signal that gives you your navigation on your phone can be impacted every single day, not just during big events, but anything going on. Humanity is in space so much more than even we were 5 years ago. So we are feeling the impacts of space weather in ways we've never had before.
The atmosphere of the Earth has different layers, and there are ones that are very close to the surface of the Earth, and then they go further and further out. The one at the very outer edge is the exosphere. Exo is the fact that it's connected to the exterior. You can think of it as the exterior of the Earth's atmosphere. And that's where you start to get undense or not dense, and you move into outer space.
During active solar conditions, the exosphere actually plays a really critical role in Earth's response to the large disturbances that the sun can put off, known as coronal mass ejections. And when they hit the Earth's magnetospheric bubble, this bubble formed by the trapped plasma populations and also Earth's intrinsic internal magnetic field, they can greatly change the ion energies, the magnetic field configuration. And what the exosphere does is that because of this charge exchange process, whereby the ions and the neutral exospheric hydrogen atoms can collide and it creates a hot neutral that enhances escape, well, the other thing it creates is a cold ion. So this is the critical process by which the magnetosphere loses that excess energy that it gains during these solar storms. Before the Carruthers mission, humanity had only acquired 4 images, single images acquired as an opportunistic photograph taken by a particular sensor that had other science goals, 4 images of the Earth's exosphere where it actually fills what's called the field of view of the camera. It fills the whole picture. What the Carruthers mission will do is for the first time have a dedicated exospheric imaging platform. So we'll not only get to the ideal vantage in space where we're able to take these wide field pictures, but we won't do it just once. We'll be doing it 3 times every hour for years. And so we'll be able to create essentially movies, watch a video of how this atmospheric layer responds when a storm hits. Watch it change with season over time when the sun is being quiet. And this is really going to revolutionize our understanding of both the exospheric structure, but also its dynamic response to the space weather.